Hello everyone. Okay, so we're supposed to have a class on Friday, unfortunately, due to the Musu general elections. We had a holiday and we couldn't meet. However, instead of us just meeting on Monday to do what we are supposed to do on Friday, I decided that I do the recording because the part that was remaining was just something that is short. So here is the recording, and I hope that you find time to listen and watch this recording so that you are up to date as well. And then as we meet on Monday, then we'll look at something else new. All right, so we were solving partial differential equations, and initially we looked at solving partial differential equations using direct integration. And then later on, we also looked at how to solve partial differential equations using the Lagrange's method. In this session, we are going to look at how to solve the same partial differential equation, but this time around, we'll be using separation of variables. Now, separation of variables works, but sometimes, of course, it doesn't work. For example, if you have the heat equation, wave equation, the process equation, so you find that the separation of variables works very well. Now, to use the separation of variables, it is important that you also remember on how to solve the ordinary differential equations. Okay. Now, if it happens that the ordinary differential equation is just of first order, then that one is very straightforward. You can just use direct integration and then you have the solution. However, if the ODE is of second order, there is the issue of coming up with the auxiliary equation. Now, the auxiliary equation results in three situations or three cases. Okay, so like I said, if it is of first order, it's straightforward. Direct integration works, and then you have the solution. But if it is of second order, then there's need to come up with the auxiliary equation. Now, this auxiliary equation, which is shown here, arises into three situations, okay, or three cases, yeah, because you see, this is just a quadratic equation, and then you expect three cases. You can have equal real roots, or maybe you can have distinct real roots, or you can have complex roots for this quadratic equation. So in that case, we have the three cases as follows. If it happens that the auxiliary equation has two real distinct solutions or roots, okay, then you expect the solution of this differential equation, this ODE here, to be this one here, okay, where of course C1 and C2 are just constants, and remember M1 and M2 are roots of the auxiliary equation. Okay, the second situation, it's when the roots are repeating, or the equals, yeah, M1 equal to M2, which we just pick it as M, then you expect the solution to be like this. Of course, here, I think this is a typing error here. There should just be one X here. Okay, take note of this. And then, as before, C1 and C2 are just arbitrary constants. However, if it happens that the solution to the auxiliary equation of complex, then you expect the solution to our differential equation up there to be in this form. Okay, so you see that it will have is the cosine and sine. Okay, all right. Now, let us look at some examples. So before we even look at examples, you need to remember this as you are solving. So you will see if you have once you do separation of variables, you have the ODE. Now you check if the ODE is of second order like this one, or it will be just of first order. First order meaning this part here only there. So first order, where the highest power of the derivative here is just 1. Okay, that is of first order. Yeah. Okay, so let us look at an example here on how to solve a partial differential equation using separation of variables. So I want to solve a partial differential equation using separation of variables. Okay, so okay, let me get the board. Now you see here we have du dx equals 2 du dt plus u. Du dx equals 2 du dt plus u, and we are given a condition that u, the function u, is equal to this one when t is 0. Okay, when t is 0 here, then the function is just equal to this. So we want to solve this. We want to look at how do we solve this kind of equation. Okay. All right, let me get the board here. Okay, so our partial differential equation is of this form: du dx equals 2 du dt plus u. This is what we are given, and then we are told that u x comma 0 is equal to is it 6e negative 3x. This is what we are given, a condition. Yeah, condition here. This is a condition. Condition. Okay, now I didn't mention, but I wrote in the slides, if you read through, when we are using separation of variables, the assumption is that the solution to a PDE is just a product of two functions, the other function depending on x alone, and then the other one depending on t alone, depending on the variables that are there. In this case, we are looking at x and t. Okay, so having that in mind, we make an assumption to say, okay, let the solution this ux comma t equals to x, which is just depending on x, and t, which is just depending on t. Now allow me, going forward, I'll be just writing like this. And take note that whenever I write the capital letter X, I'm talking about a function that is depending on X alone, and the capital letter T is a function that is depending on T alone. Okay, so let this be the solution. Yeah, be the solution. Okay, if that is the case, it means that it should satisfy this PDE. So what do? We substitute in there. Okay, where there is u, we put this. Okay, so we have d. So here where there is u, we are going to put xt. Okay, dx equals 2. Where there is u, again, we put this one here. And then dt plus, where there is u, again, we put this like this. Okay, so now once we do this, then first of all, we just do just normal differentiation. T here, because we are differentiating with respect to x, so t is treated as constant. But now you can see that x is just depending on x alone, there's no t, so this just becomes a normal derivative of x, and then dx like this equals 2. Again here, it is depending on, we are differentiating with respect to t only, so x can come outside, and then we have dt, and then dt like this, and then plus xt like this one. Okay, now after doing that one, we can now divide through, okay, through by xt. Okay, we divide through by xt. So the moment we do that, then we expect the first one here to have 1 over x dx over dx like this equals, we have 2 1 over t, and then dt, okay, dt small letter t like that, and then here it will be just 1. You see that? So there it will be just 1. All right, so what do we do now? We say, okay, because if we are saying that this one here is equal to, let me just scroll down a bit so that we see like this. If we are saying that this one is equal to this, then we can let it equal to some constant alpha, because this depends on x, this depends on t, then it must be equal to something which is common, and that can be only constant. Yeah. Okay. If that is the case, then we'll get now the first part here, 1 over x dx dt, dx again, sorry, and then equal to alpha. Okay. And then this implies that 1 over x, so I want the one with the capital letter X to be on one side, and then the other one with small letter x to be on the other side. Now this is just of first order, so we are using direct integration. So if we integrate here, just integrate like this, yeah, no more integration. So this will be ln x equals, so you have alpha x plus, now we have a constant here. Now looking at ln x here, we can use ln to come up with a constant, say ln k, for example. Okay, still a constant. And then once you bring this ln k this side, then you are going to have and apply the exponential function, then you are going to have x over k equals e alpha x, like this. Okay, so that is, you take this aside and then you introduce the exponential function, so it will be ln of this, like this. Okay, maybe I was like this. Okay, like ln of x over k equals alpha x. So once you introduce the exponential function here, you find that this will come down, so it will be x over k, and then you have e to the power alpha x. Okay, and this implies that x is just equal to k, e to the power alpha x. So that is our x. Okay, so that is our x. Now we need t. So we have x, now we need t. Okay, now we need t. So the other one is like this. For t, it's 2 1 over t, like this, dt dt, like this, or plus 1 equals alpha. So now this implies that, so you take this one this side and you divide by half here, 2, so that would remain with 1 over t only. So it means I'll have 1 over t only here remaining with this dt. Okay, for now let me write this dt so that people can see properly. Then I have 1 over 2 because I divided by 2 throughout, and then here you have alpha minus 1, like this. Okay, and then this becomes 1 over t dt, like this, equals 1 over 2 alpha minus 1, then this small dt goes this side. And then again you just integrate, it's direct integration. Once you integrate, and then you have this side here, you have ln t equals, we are integrating with respect to this t here, so it will be 1 over 2 alpha minus 1, and then t, like this, and then plus some, again some arbitrary constant, let's say ln what, ln anything, you know, ln a, for example. Yeah, it can be any number, any you can use any letter here, it's up to you. Okay, so now once you do that, once you do that thing, then it means that, like before, this will be t over a, like this, is equal to e to the power half, and then you have alpha minus 1 t, like this. Yes. Okay, and then this implies that t is equal to a e half then alpha minus 1 t, like this. Now that we have got both t and t and x, this t we have, x we already found here, then we can now write u. What is u? U of x comma t is equal to, so our x, remember it was a product of xt, so it's k e alpha x, then this one is a e half, and then alpha minus 1 t. Okay, now e is common, so I can write ka e, so I can write alpha x plus half alpha minus 1 t, like this. So we have something like this. Okay, and then after finding that one, we need now to apply the condition. Okay, so the condition that we are given is that u x when t is 0 is equal to, we are told that this is x6 e negative 3 x. Okay, that's a meaning, yeah. And then now if we substitute in here, where there is t, we put here, where there's t, we put 0, then this becomes k a e alpha x. Okay, now what does this mean? This one, it means that ka is just 6, and this alpha is just negative 3. That's a mean. If you compare the two, that's a mean. Okay, and then if that is the case, then you just substitute. You have u xt, you substitute in this u xt, which is here, so you have 6, then e, then you have 3x plus half, open bracket, okay, not 3, it will be negative 3 because we found alpha is negative 3 here, minus, open bracket, minus 3 minus 1, okay, and then close bracket t, like this. Okay, and then that's all. You just simplify. You have 6 e minus 3x. Now this is negative 4. Negative 4 divided by 2 is negative 2. Yeah, so negative 2t. Okay, so that is our solution. That's all. It means you're done. So you see that solving this is not that complicated. Of course, it may look like it's some there's a lot of, not very much, but it's something that is easy to follow. And then you find the answer to be this one. Yeah. Okay, so this is how you can solve a partial differential equation using separation of variables. So it's first example. Let us go to another example. Okay, so this is what we are doing, and yeah, so let us see. Okay, so it has to arrive at this. So we arrived at this. This is the answer. Okay. Okay, so now alpha, like here we picked, we picked alpha, of course. So when you're picking it, you pick the one that works. Okay, and then it can be plus or minus, it depends. Okay, yeah, so it's up to you on how you pick this. You just pick the one that works. Okay, and the one that is very convenient, you know. So you look at the thing that you have come up with, and then now you decide, okay, which one should I pick here, and then you make sure that as you are picking, it's something that will be workable. Yeah. Let us look at another example here. There may be a few examples that we need to look at, and then we'll just call it end there. And yeah, it means the lesson on Pdes is done. Okay. Again, another one. Yeah. Use the method of separation of variables to solve the equation, this one. Now, if you look at this, this is, it has got two things. Yeah, it is of second order in x and it is of order 1 in t. Okay, and we are given some conditions. Given that t is 0 when t is approaching infinity, as well as v is equal to 0 at x equal to 0 and x equal to L. Okay, so we want to solve this partial differential equation. Now take note, in x is of second order and in t it's of first order. So all of it, in short, it's of second order. Yeah, but once you do separation of variables, and then you'll be able to see on how this works out. Okay, so let us go to the board again. We'll try to do this. Okay. Okay, so we go here. Example, or maybe the second one, we can call it the example 2, the other one I didn't write. Okay, so it was d squared v, is it v? Yeah, dx squared equal to dv, is it dt, something like this, dt, yeah. Now, we have v equals 0 when x approaches infinity, and then we also have v equal to 0 when x is equal to 0 and x equal to L, like this. Okay, so this is these are the conditions. These are conditions given. Yeah. Okay, so as before, we are using separation of variables. So the first thing, let v, in this case is vx comma t, there is x and t, equals, so we have x then t. Remember, this is function of x alone and this is a function of t alone, and then substitute in the partial differential equation. So we have 2 like this, xt dx squared equals xt like this, dt like this. Okay. Once we do that, then this is we're interpreting with respect to x, so t is constant, and then this just becomes like this now, like this, equals, again here it's with respect to t, so you have x dt, like that. Now, here we'll differentiate, we'll divide by xt, this capital X and capital T. Yeah. Once you do that, so divide by xt throughout. Yeah. So once you do that, you're going to have 1 over x. Okay, and then d like this equals 1 over t dt. Why are we doing this? We are separating variable one, those with x to be on one side and those with t to be on the other side. That's why we are doing this. Now, it is at this point where you need to equate it to a constant. Yeah. So in that case, we're using alpha. Alpha. But then now, because we have okay, this is part of it. We have this one which is of second order. You see, once you equate it to something, then we are coming up with an auxiliary equation. Now, we want something that will be able to work for us as we are doing this auxiliary equation. That will be easy for us to solve. Okay, so in that case, we can introduce a constant which is negative throughout. Okay, now how do we introduce the negative constant here? Okay, so I can say, okay, my alpha will be in terms of so I will say alpha squared. Okay, so alpha is just any real number. Okay, n real number, but then we have put it squared, so it's positive, but because of this negative, so it's always negative. Yeah, so this is a negative constant. It's for easy computation when it comes to solving this. Okay, so that's why we are picking that. Like I said initially, you pick the one that works. You pick the one that works. It's not just about just picking, you know, but the one that you feel, oh, okay, this will work. And then you pick the one that works. Yeah. Okay, so having done that now, then you can pick them pairwise. Yeah, it means you have two things now. Yeah, you have two things. So you have the first one, it's 1 over x dx, okay, with a square here, dx squared equals negative alpha squared. Okay, now this one implies that this is d, like this, dx squared. If I bring that this side, it will be alpha squared with an x here equals 0. So I have multiplied throughout by x and then brought the other one the other side. Okay, so it becomes like this. Now this is a differential equation, ODE of second order. So we need the auxiliary equation. So yeah, so the auxiliary equation for this one, it will be m squared plus alpha squared equals 0. Okay, so you can compare the auxiliary equations up there. Then you see that it will be this. Now, once you solve this auxiliary equation, when you solve it, it implies that m will be equal to plus or minus I. This is complex number, yeah, I alpha, like this. Okay. Now, we already talked about how it looks like. It means that now our x in this case will be equal to, now e, okay, here there is no number, so it's a 0. So e power 0 is 1. So we have constant. Now I need to pick constant. So I can say a cos alpha x, this is x, yeah, plus b sine alpha x. So this will be our solution for this ODE, this one here. Okay, so we have x. Now we need to get t. Okay, now for us to get t, we have here this one here, 1 over t dt like this equals negative alpha squared, like this. Yeah, then this one now we can just use, because this is your first order, yeah, we can use direct integration. So this implies that 1 over t dt is equal to negative alpha squared, and then now you have the small letter t, like this. So that we are setting it to for it to work with direct integration. Once you integrate directly, this one you have ln t equals this will be equal to what? It will be equal to negative alpha squared t, like this. Yeah, then plus some arbitrary constant. So arbitrary constant here, I can use which letter? So I'll say ln. Which letter should I use? I used a b, so I can use c, for example, like this. Okay, and then we have already seen how to do this one. So this will be just t equals c e to the power negative this. Okay, now that we have both x, we have x here and we have t here, so we can write what v is. So meaning v of x comma t is equal to, so I'll start with this one here, or I can put it in its bend, or I can write a cos alpha x plus b sine alpha x, like this, then c e power negative alpha squared t, like this one. Okay. Are we done? No, not yet. Remember, we have conditions that are given. So we are not yet done. Okay. So the first condition. So we are going to use, let us first of all use the this condition when x is 0, v is 0. Okay. We are told that v of 0 comma t is just equal to 0. That's what we are told. Okay, and then this will be equal to, now where there is x you put 0, so here there's an x, I put 0, I put 0 here, so this one sign 0, it becomes 0, but cos 0 is 1, so I'll have a remains inside here. This one has no x, so c e negative alpha squared t, like this. Okay. That's a meaning, yeah. Now, after doing this, then what does it mean? Yeah, it means this letter c here, okay, because we are saying that this is 0, but this c here, you see the c, let me just change the color. This c, this cannot be 0. Why? Do you know why? Okay. Anyway, in case you don't know, if c is 0 here, it means the O of this becomes 0, and we don't want a trivial solution. Okay, so we cannot go with a trivial solution, so c cannot be 0. Yeah, so if this is equal to 0, but c is not 0, again, you see the exponential of this cannot be 0. Yeah, so it means that a itself must be 0. Okay, that's a meaning. That's a meaning. It means that this implies that a is 0, since c can never be 0. Okay, it's not 0. Yeah, if it is 0, yeah, it's a trivial solution. No one wants a trivial solution. Yeah, it works, of course, but that's v equal to 0 doesn't make sense. Yeah, because it's very trivial. Okay, now if a is 0, what does it mean? It means now v of x comma t is equal to, so a is 0, so this goes, so we can have b with c. Okay, allow me to write this side like this, then sign alpha x becomes the solution at this point when you apply the first condition. Okay. The other condition that we have is that when x is L, this is also is 0, v is 0. So when x is L, v is 0 also. So x vl comma t is equal to 0. That's what we are taught. Now this equals, so where is x, we're putting L here, where is x. So we have b, c, e negative alpha squared t sine alpha L, like this. Okay, is equal to 0. Now again, b cannot be 0. Okay, c we have already established is not 0. Again, b cannot be 0. Do you know why? We have already said that a is 0 from this one. If a is 0, then if b becomes 0 also, again we go to trivial solution. That's what, it's not what we are looking for. Yeah, so b cannot be 0, so b also cannot be 0 here. B cannot be 0. Yeah, and c already cannot be 0 because we have already said that. So what does it mean? It means that sine alpha L is the one which is 0. Now this implies that it is equal to sine n pi for all n natural numbers. N natural number. Okay, when n is a natural, 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. So this is 0. Yeah. Okay. Now what does that mean? It means that alpha L is equal to n pi. Now what does it mean? it means that alpha is equal to n pi over L. That's the meaning. Alpha is this. That's the meaning. N pi over L. That's the meaning. That's our alpha. Okay, if that is our alpha, then we know now that v of x comma t will now be equal to this bc, okay, e to the power negative. Now alpha we have said is n pi over L, so n pi over L squared t, like that, as a power of e. Then sine. Again, here where there's alpha, we have n pi over L x. Okay, and if we let b c depend on some n, if you want you can stop there, but however, if we let this be any something that is depending on n, depending on the value of n, then in general we have vxt to be equal to the summation, okay, n running from 1 going up to infinity of, so bc we have said is bn like this, and then you have e negative n squared pi squared over L squared. Okay, so this must be L squared and then t. Okay, and then we have sine n pi over L x, like this. So this becomes the solution. Okay, so that's how we get the solution. It's a bit involving a bit, but yeah, it's something that is straightforward to do, unless otherwise, unless otherwise. So the solution becomes like this, where this is L here, L squared down here, you see. So that's how we do that one. That's how we can solve that partial differential equation. Okay, so yep, so this is the solution for this one, you see. Okay, so yeah, it will run here. Okay, so it's this. Okay, yeah, so there we have, yeah. Okay, so the letters used are different, so I was using alpha. There's p here, so it's fine. It's one and the same thing. You can use n later, yeah. In the end you have this, which is exactly the same, yeah. Except that here there's typing error, so this L is not over everything here. Okay, so take note of the typo error here. It should be like this. So there's a typing error. This L is not over everything including sign, so the L is just over this n pi x over L. Okay, that is clear. Yeah, let us look at the heat equation. The heat equation, yeah, this is the heat equation. On the heat equation, we want to solve, again we're using separation of variables, solve the heat conduction equation, this one. Now it is over x is from 0 to 3 and t is greater than 0. And then we have the boundary conditions. So this is this x now here. Look at this. This is the heat equation. Okay. So the x, you look at it as the length. Yeah. This is the length. So it's the length from 0 to 3. Okay. That is our x here. And then this t is time. Yeah. Time taken. Yeah. Which is greater than 0 here. Yeah. So when you're talking of boundary condition, it's the length from 0 to 3. So you check at 0, what is it? So we are told that at 0 it's 0. U is 0. And U, this U, think of U as the temperature, because this is the heat equation. So this is the temperature here. Okay. So at 0 here in the boundary, these are boundaries, yeah. At 0 here you have the temperature 0, and at 3 the temperature is also 0, so the temperature is the same. And then we are given the initial condition when t is 0, yeah, when time is 0, the temperature is given by this. Okay, so this is how you should think of the heat equation here. You have U, the temperature, x is the length, and then t is the time. Okay, and then you have just a constant here, scaling constant, yeah, which we can think of this as maybe diffusibility, diffusibility of this. So you'll find that if you were to simulate and try changing this constant here, you will see how it will be behaving, yeah, how the temperature will be behaving, this temperature for this one here. Okay, but then we are given it's not just it's not a variable here, it can be a variable, yeah, it can, so that you check what happens as we are changing the value of this diffusibility constant, yeah. Okay, so our interest here is just to solve. Okay, we just want to find what is U, or what is this temperature, yeah, with these conditions for this heat equation. That's our interest here. Okay. Okay, all right. So let us go to it. We go to the board. So let's see this one/1/2. Okay, and then we have this. Okay, let us go to the board and we try to solve this. We can create example number maybe 3. Okay, column number 3. So we had d squared u dx squared, and we had 1/2. That was du dt. Now we are given conditions. Okay, we are told that the length should be between 0 and 3, and then we are given the boundary conditions, the boundary conditions, yeah, where you are told that u at x0 it is exactly the same as u at x3, and this is 0, the boundary conditions. Then we have the initial conditions, yeah, initial boundary initial conditions, yeah, not initial boundary, but initial conditions, yeah. So you have when time is 0, we are given when time is 0, we are given that this is defined by this 5 sine, okay, 4 pi x. So these are the things that are given here. Okay, so let us go into it. Let's try to do it. Okay, so now we are using separation of variables, so just as before, that's the first thing. So that's why this is one easy method to use, yeah. Just late. Okay, it's u, we are dealing with u. So u, okay, now I'll just write u. It depends on x and t, so allow me to write it just like that, and then I'll write like this. Okay, let's substitute in this PDE. Then you have xt dx squared equals 1/2 xt dt. Yeah, so this is the heat equation, yeah. Okay, Okay. So now, once you do this, then you just do the usual things. This is with respect to what? To x, so you have d squared x, dx squared equals 1 over 2. You have x dt, like this. Okay. All right. After doing this, then you can now separate variables, yeah, by just divide throughout by xt. Okay, xt. Once you do that, you have 1 over x d squared x dx squared equals 1 over 2 t, actually to come here, then dt, like this. Yeah. And then, like before, because of this, we pick the negative number. Yeah. So we let this equal to some negative number. Should I use alpha? Maybe let me use lambda squared. We can use anything, alpha or lambda squared, anything, it's up to you. But then we are taking that this lambda is any real number. So this lambda here, it's any real number. And then once we square it, and then with a negative, so we know that this is negative here. Okay. And then now we solve. Once we solve this, we have separate, yeah. So we have 1 over x dx squared equals negative lambda squared. And then once we write this properly, dx squared plus lambda squared x equals 0. Okay, that is for x. And then auxiliary equation, lambda squared equals 0. So m is equal to plus or minus I lambda. Okay. And then that gives us x equals constants. I'll use a cos lambda x plus b sine lambda x. Okay. Okay. Then the other one, which is 1 over 2 t dt like this equals negative lambda squared. So this is 1 over t dt equals negative 2 lambda squared dt, like this. Okay. So this is lim t equals negative 2 lambda squared t plus b. Or use what constant? I use ab, so I use c, so that we have t equals c e negative 2 lambda squared t, like this. Now we have two solutions. So we know how u will look like. So therefore, that's u x t will now look like this: a cos lambda x plus b sine lambda x like this one, then ce minus 2 lambda squared t, like this. So it will look like this. Allow me to just expand this one, this constant c, bring it inside here. If I do that, ac, I can write it as d cos lambda x, plus bc, I can write it as e sine lambda x. So that now we reduce on constants, lambda squared t, like this. You see? Now we start applying conditions. Okay, that's where we start now applying conditions. So we start with the boundary conditions. Okay, so boundary conditions, apply boundary conditions. So u at 0 t, we are told this is 0. Okay, so it means where there is x, you put a 0. So if I put 0 here, this is d, this will be d, this will be 0, so that is e negative 2 lambda squared t. Okay. Oh yeah, yes. Okay, that is correct. Then once we do that, it means only d can be 0 here, so it implies that d is the one which is 0. You see, because this cannot be 0. So in that case, our u x comma t now becomes, because d is 0, so it is just that one, e sine lambda x e negative 2 lambda squared t. The writing here not good. This was supposed to be the other way around, but it's fine. And then again you apply another boundary condition. We are applying boundary condition, so it's u 3t. Again we are told this is 0, so if that is the case, you put where there's x here, you put 3, so this is e sine 3 lambda, then e minus 2 lambda squared t. Okay. Now e cannot be 0, because it means the O of this equation becomes useless, because it means it becomes 0, so it means this is the one that must be 0. So this implies that sine 3 lambda is equal to 0. Now we know what this means. It means that sine n pi is equal to 0, like this. Okay, where of course n is any natural number. Okay, and then once we do that, then we know that 3 pi is equal to n, or 3 lambda is equal to n pi, and this implies that our lambda is just n pi over 3. Okay, if that is the case, then now our u x comma t becomes, so at this point we still have e, so we still have this e, it's here, we have not found what e is, so e is still there. Okay, let me now start with this, because initially I started. So lambda we have found, it's n pi over 3 squared, and then t, like this, and then here we have sine again, lambda is n pi over 3 x, like this. Here we substitute. Okay, and then after applying boundary conditions, now we apply initial condition. Okay, the initial condition, it says u of x, this 0, is given by 5 sine 4 pi x, like this. This is the initial condition given. So what does it mean? We substitute here in this one. Where there is t, we put 0. So once we put 0 here, it will be e power 1, and then e power 0 is just 1, so it will be e. Okay, and then sine n pi over 3x. Now if you compare the two, it means that e is equal to 5 and 4 pi is equal to n pi over 3. Now what does it mean? It means that n is equal to, let's see, it's 12, so it's 12. N is 12. Okay, so if n is 12 and e is 5, then we can substitute in here. Okay, therefore uxt is equal to 5, where is e? Here we put 5, and then we have e to the power negative 2. Here we have 12 pi over 3 to the power 2 t sine 12 pi over 3 x. And then what is this? So 3 into 12 is 4. 4 power 2 is 16. 16 times that one, so we have 5 e to the power, so 16 times negative 2 is negative 32 t. Okay, pi squared t, like this. Then here sine 3 into 12 is 4 pi x. Yeah, so this would be the answer. That's all. Anything missing? No. So this would be the answer. Okay, so you see how this works out. So to be frank, this is very easy. I think it's something the easiest one can do. Here there's nothing complicated. It's something that just follows very straightforward without any challenges and the like. So this is what you get. It means we have found our solution for the PDE. This one we are finding for this one here. So let us see what is there. Okay, it's a lot that was written. Okay, yeah, so we are here. Okay, so here we are. Yeah. Okay, it's the same thing. The wave equation. Okay, solutions will be done in class. Okay, so we have this wave equation. Find a solution. Now this one, you see that there are no boundary conditions, there are no initial conditions, so we expect the solution to be in general form. Okay, so for this one we expect the solution to be in general form. So let us try to do it. So this is u dt and then c2 u dx. Okay, let us go to the board. U dt. Okay, we are starting with u dt. So this one is number what? Maybe number 4 for today. So this is like this one, equal to c squared. This is u, then x squared. So this is the wave equation. So no boundary conditions, no initial conditions. So we expect just a general solution for this one. So it should be very straightforward. However, you need to practice those which have got boundary conditions, initial conditions, because those are the ones that can be, maybe those you can meet them as well. Yeah. Okay. So again, like before, it's u here, so it's u. Okay, u. Now let me remove this. Equals xt, like this. Substituting there, you have, oh no, you have xt like this, t squared equals c squared xt like this, dx squared. Okay. All right, so like before, this is with respect to t, so I will remove x, then this becomes just like this, equals again c squared, what comes out, t d squared x dx like this. So it comes out to this. Now when we are dividing, separating variables, now when we are separating here, we don't want a situation where when we are dealing with auxiliary equation we have this constant c squared. So we'll divide. So what we do, divide by xtc squared. Okay, so we want to get rid of this, not to be a constant of this one, because when we are finding auxiliary equation, we don't need this to have a constant. Okay, so once we do that one, it means that now here it would be this c squared t dt dt like this, you see, equals then here 1 over x dx d. Okay, this should be squared here, squared like this. Okay, so it's to avoid this one having a constant here. Okay, and then like before, we equate it to a negative constant. Yeah, so negative constant, let's say negative lambda squared. I think that's one we're using, or whichever, yeah, lambda squared. You can pick any constant here. Okay. That done, then the first part here we have 1 over c squared t d squared t dt squared equals negative lambda squared. Okay, now what will this become? It will become d t dt squared plus c lambda squared lambda squared t equals 0. You see, just multiplied by this throughout becomes this. So you see that there's no constant here. This is what we're trying to avoid even for x here. If you left it here, you would be stuck when you're picking the auxiliary constant, the auxiliary equation. Okay, and then the auxiliary equation for this one, it's m squared plus c squared lambda squared equals 0, and then the solution is m equals plus or minus I c lambda like this, you see. And then now t will be equal to constants. I'll pick what, a cos c lambda t plus b sine c lambda t. Okay, also here you have, once you do this one, everyone should be able to know how to do this. It will be d squared this plus lambda squared x equal to 0. Then you accept lambda equal to plus or minus I, or sorry, m equal to plus or minus lambda like that. Then x will be equal to, well, use which constant? I use the ab, so I can use c. I don't know whether that is good, because I already have c here. So allow me to use I'll use what? Constant hard to find. Q. Okay, P. Okay, so P cos lambda x plus Q sine lambda x. Okay. So therefore our U will be equal to A cos C lambda t plus B sine C lambda t times P cos lambda x plus Q sine lambda x. So you stop here because there are no conditions that can help us to find these constants that are there, because we are not given in boundary condition, neither were we given initial condition. So nothing was given, so we leave it as a general solution like this. Okay. Okay, so yeah, this is this. So yeah, don't worry about the constants. They can be, yeah, depending on how they were picked, you see. But what is important is here, you see, the same. And I think this one, I don't know, you can check in your slides if I think there was a typing error. Maybe I corrected this later on. You can check here if it is this. Okay, check in your slides, and then if not, you can just correct it here. Okay, now this is the Laplace equation. Yeah, okay, yeah, this try to do it as an exercise, but please try to do it, otherwise anything can happen. Yeah, so try to do this as an exercise. Check if you can do this. The Fourier series, like I mentioned last time, will not go into details of this. I gave one example. You can maybe go through it at your own time. Yeah, but maybe we'll just we may not use Fourier series. Yeah, so for now just use those that we have done. All right, so we'll end here for today, and but try to do this. Yeah, I know you already know how to do Fourier series, so that one shouldn't be very difficult when it comes to using Fourier series. We did Fourier series in EGM 311. Okay, everyone knows how to do Fourier series, so you can just check on what we did in EGM 311 on Fourier series, just these computations on Fourier series, and then apply them in solving the partial differential equation here. Okay, thank you very much for your time, and I hope that this was helpful. So next time as we meet, we shall start looking at something new. So I will share that also in the group. I'll share this video, of course. It will be there, and also the topic that we'll start looking at on Monday. Thank you very much for your time. Enjoy your day.